is cooking, all you lovely individuals? Welcome back to Math. And today we're going to be taking a little bit of a smaller episode, hence the 12.5. It's more of like a commentary on the last video. In the last video, we were using factor trees in order to find the prime factorization of numbers, basically figure out kind of like the atoms that made up all of our numbers, and factor trees were the method we used for that. And in that video, we did something like the follows. So let's say I wanted to factorize 28. So we're finding the prime factorization of 28. So we start with 28 and we split that up into 2 and 14 because 2 is the smallest prime number that we can chunk off from this. And we look, okay, what's the smallest prime number we can chunk off from 14? And we get 2 and 7. And these are both prime numbers, so we'd be good to go. So the prime factorization of 28 was 2 times 2 times 7, or if we wanted to write it in an exponent form, it'd be 2 squared because we have 2 multiplying by itself twice, times 7. All right, so this is what we did in the last time. And the kind of idea with the factor tree is we always took off the smallest prime number at every single step. But I wanted to show you in this video that that's not actually necessary. We can do it in kind of whatever order we want, and we're still going to get some meaningful information out of it. So, for example, we could try 28 again and notice that 28, that's 4 times 7. And we have taken off 7. So 7 is a prime number, great, but it's not the smallest one. But we're going to see that that's actually not going to matter here. So if I try to factorize the 4 now, 4 can split up into 2 and 2. And we see that we get the exact same prime factorization as before. And so what I want to emphasize is that we can basically do this in whatever order we want, not just in the smallest to biggest order. This method where we go from like the smallest primes to the biggest primes, that gives you kind of just a nice structure to follow, but it's not necessary. You can kind of just factor a number into whatever pieces you feel like, and if you keep breaking it down into the primes, you're going to get the same thing. And this follows from the fact that the fundamental theorem of arithmetic says that the prime factorization of a number is always unique. It'll be a unique combination of prime numbers that gives us this. So if we break a number down into primes, it doesn't matter the path that we take to get there, we are still going to get the same factorization. So let's try another one. Let's go with factorize 520. All right, so first of all, I'm going to do it with the method that we all know and love by just chunking off the smallest prime factors. So we're going to get 2, and 2 times what is 520? It'll be 260, right? 2 times 200 is 400, 2 times 60 is 120, 400 plus 120 will be 520. So that's how I know that 2 times 260 is 520. So we got our first 2. 260, that's even again, so we can chunk off another prime factor of a 2, and we'll get 130, since 2 times 130 is 260. But lo and behold, this ends in a 0, it's even, so we can chunk off another prime factor of a 2, and we can note that 130 divided by 2 is going to be 65. So we get 65 out of it. Now we can keep going here. So does 2 go into 65? It doesn't, right, because this is odd. How about 3? That's the next biggest prime number. Well, we can check 3. We get 6 plus 5 is 11. That's not a multiple of 3, so neither is 65. So we can't do 3. What's the next prime number? 5, right? And we know 5 goes into this because this ends in a 5. So we can chunk off a 5. And 5 times what is 65? Well, it's going to be 5 times 13. And 13 is also prime. So we get our prime factorization of 520 is 2 times 2 times 2 times 5 times 13. And we can also write this in exponent form as 2 cubed times 5 times 13. Sometimes it's not always the most convenient to just chunk off the smallest prime number. For example, maybe you weren't super comfortable with doing 520 divided by 2 to get 260. Maybe that required a bit more brain power. Or maybe you weren't sure what 65 divided by 5 was, so maybe you had to do long division to figure out it was 13. So it might be helpful to just kind of be able to take off the obvious factors every single time. So let me do this again, and I'm going to show you that we're going to get the same thing. So let's start with 520, and I'm going to split that up into 10 and 52, right? We know that 10 times 52 is 520. Maybe this is a more obvious factorization we can do. Now notice, neither of these are actually prime numbers. But that's all right. As long as we just keep factoring the composite numbers, we're going to eventually get to the same prime factorization. So if I do 10 and I split that up, I'm going to get 2 and 5. And those are both prime numbers. All right, and now we can focus on the 52. Well, 52, I know I can split that into 2 and something else. It'll be 26. And so we recover our 2 out of that. And 26 we can split up into 2 and 13. And notice we get the same prime factorization as before, right? We have 3 2's, we have a 5, and we have a 13. So it didn't matter the method we actually did it. We got the exact same thing. So let's try and factorize 520 in an even different way, and we're going to see we're going to get the same thing still. So maybe do that over here. All right, so we'll start with 520. And this time, I'm going to maybe do the first thing I did before. So 2 and 260. And then maybe I'll split 260 up into 10 and 26. Right? Because 10 times 26 is 260. We can split the 10 up into 5 times 2. And we can split the 26 up into 2 and 13. And these are all prime numbers. So we're going to get the exact same prime factorization again, right? We have 3 2's, a 5, and a 13. So the point of this video, and again, it was a really short video, but the point of the video was basically to say that you don't have to follow the structure of a factor tree where you need to break off a prime at every step, or it doesn't even have to be you need to break off primes in a certain order where you're always starting with the smallest. As long as you're just factoring the number into 2 pairs that give you the previous number, eventually you're going to have no choice but to come down into these prime factors. And that's guaranteed by the fundamental theorem of arithmetic. Because every single number, when you break it down enough, it's going to be all primes. It's primes all the way down, baby. So have a good one, stay groovy, and I'll see you in the next video.